Okay, so Peter, should we start? Okay, I think we should start. It's already 10:30. So hello, everybody, and welcome to this first session on rotary scroll and screw compressors. Let me just very briefly introduce myself. My name is José Corberán, and I'm professor at the Applied Thermodynamics Department at the Universidad Politécnica de Valencia, and I'm going to chair this session together with Dr. Sam Rane from the City University of London. So we start already with the first presentation that will be given by Christian Berin. So, Christian, could you launch your presentation?
Yes. I am not allowed to share my screen yet, so maybe someone needs to grant me permissions.
Okay, just wait some seconds. Maybe they have to. I don't think it is me. I hope. I have the button for sharing the screen.
But
you don't?
I don't have.
Do you have a problem here?
I cannot share my screen yet.
Okay, please try now.
Yeah, that's perfect.
Okay. So first presentation will be given by Mr. Christian Berin, and you have the title on the screen. So please, Christian, go on.
Yeah, dear Professor Corberan, thank you for the kind introduction and welcome to the audience, dear ladies and gentlemen, dear colleagues. I'd like to welcome you all to my presentation with the title Influence of Refrigerant and Compressor Construction Forms on Efficiencies Assessed on Dynamic Simulation Models. And yeah, one could ask the question, why another compressor model now? And let me take the further 12 minutes to show you why we use the further compressor model. If we already have seen in the introduction of this conference, we maybe more or less again have the question about which refrigerant should we take now. We all know we started using natural refrigerants, then we went through safety refrigerants to low ozone depletion potential refrigerants. Now we are in times of low global warming potential refrigerants, and increasingly strict political regulations more or less force us to look at alternatives which are where we have the permission to use in the future. And besides all those things that we need to ensure, like thermodynamic potentials and states, we have the political regulation, and we have the wide range of applications, which is increasing as well. So we have our refrigerant cycles within HVAC and air conditioning and refrigeration. We have the automotive sector using refrigerant cycles, and we are trying to use Carnot batteries for storage systems, and almost there are refrigerant cycles in it. Compared to static loads, which were assessed before, all these processes have dynamic loads, and this requires a dynamic analysis and a dynamic assessment. For example, we need to find for new refrigerants the right oil for the compressor. So dynamic analysis allow us to look at the discharge temperatures at certain boundary conditions in our process, or we can find minimal and maximal pressures which might influence the construction form of our compressors. So these are all kinds of things we want to introduce with our simulation model right now. And summing these requirements up, we have an evaluation of refrigerants with respect to its dynamics. We want to model our behavior physically, so a physical compressor model is crucial to assess the potential of refrigerants correctly. And we want to consider real gas behavior of fluids, which might influence our results. And here we chose Modelica, and we have an example with a rolling type compressor, because Modelica is able to cover dynamic systems, which is quite helpful for us because we don't need to solve the differential algebraic equation systems by ourselves. And two modeling approaches to introduce where we distinguish between, we have on the one hand side the design modeling approaches. We use our operating point and black box, gray box, or white box models as a design model to support our design process regarding the component and geometry design. If we go the way vice versa, we have the off-design modeling with a fixed geometry, and we do the calculation for different operating points, which support dynamic assessment and controller design, let's say. So our model, which we want to present, is able to cover the off-design modeling approach, compare different effects of dynamics. We want to assess the fluid and the geometries within our model. So right in a parallel session, my colleague Stefan Göbel presents a dynamic model of a piston type compressor. So based on his mechanics and thermodynamics, I developed the model a bit further. And you can see that we're able to cover dynamic boundary conditions such as the gas temperature, the pressure, or the mass flows. And Modelica is able to calculate these transient behaviors considering different fluids, and now we are able to cover detailed thermodynamic analysis. So just, which is my part of the paper, just adjusting the geometries leads to assessment of different compressor types and refrigerants for now. So what is the goal of our model? We use the input data, and the input now is our refrigerant, the refrigerant's inlet state, and the rotational speed, which might be set by a controller. And we want to calculate the outlet state and the efficiencies of the process. And that's, let's say, the new point of our model. We can calculate the efficiencies during our process. And Stefan Göbel, my colleague, shows the approach based on Roscosh et al. For Modelica in the parallel session. And I converted this mechanical system to a rolling type compressor. And to be honest, we have some numerical issues because the geometry isn't as easy as from piston type, but we covered it and we are able to calculate all the thermodynamic states. And the next step you could imagine is modeling a scroll compressor where the mechanical side will be more complex as well. How does a Modelica model now look like? If we implement it, we have a highly modular structure, and one model always consists of several submodels. We have our geometric model, we have a compression process, we have our heat transfer and loss mechanisms, so heat transfer to the outside. And each process looks the same. We have the fluid of our inlet state, we use the thermodynamic compression, and we compute our outlet state depending on our boundary conditions. This Modelica library will be open source available, and we already introduced it to Gustav Lorenzen Conference in December last year. If you want to have a look at it, we provide a link to our Git repository within our paper. And we want to ensure by this a universal applicability, so one can change more or less easily the geometric model. We can change the compression process to a more simplified or a more complex one, and we try to do it in a modular way so changes can be made within a short time. Basically our compression process looks like this. We compute the energy and the mass balances with the real gas behavior through Helmholtz equation of state, which requires a little regression function because we haven't the density in all states, but the enthalpy and the density is a function of the temperature. And we parameterized the model according to a model in the literature. What now is quite comfortable. We don't have to solve the differential equations here by ourselves. That does Modelica for us in a solver like the Dussel solver or anyone else. So the calculations are now conducted fully automatically without solving anything before. That's part of the automation system behind the model. And what you now see is a short comparison to Mr. Goebbels' results here. Our new model calculates time-dependent changes of state for the REP, reciprocating compressor, and for our ROP, the rolling type compressor. And what you see is we are able to compare different geometries, and in the paper you will read about different fluids as well, because we have no time to show this all in 12 minutes. And you see the dynamic behavior of the system, the volume or the compression volume changes with time, as well the mass flow does. You see the pressure of our compression process depending on time, and the temperature here. We have the evaporating temperature and the condensing temperature, or pressure and temperature as well. And this leads us to dynamic calculation of our compressors. But solving all those equations has disadvantages as well. Our model's speed, or the calculation speed, decreases. So calculating those states is near to real time. So we have not the advantage of being faster than an experiment, which is not that good, to be honest. That's why we use our detailed model to change geometry, to change everything, and look how the efficiencies changed. And then we compute calculation efficiency. We compute our efficiency maps of a compressor, because such a map offers an explicit mathematical form, which might be used for any other application, which increases the calculation speed dramatically. And these are exemplified results for the isentropic efficiency above and the volumetric efficiency below, depending on rotational speed and pressure ratio. So one can see the parabolic function more or less for our isentropic efficiency depending on the pressure ratio, which is according to the literature, and a decreasing volumetric efficiency by pressure ratio, which is also according to literature. And with these maps, we now can go to high-level optimization processes, or we can go for heat pump design methods, or we can even compare it to product data. And if we compare it and say our map was valid, we can do little changes in the compressor, which was modeled in a very detailed way. And we can compute the changes in efficiency by changes in geometry, which is quite comfortable to optimize our processes with respect to different fluids. So with such interfaces like functional mockup unit, FMU, we provide you with a universal applicable simulation model, which is promising to find best fluids with respect to some applications in further studies. This all is open source within the IBIPSA Project 1, which we thank because we are part of it. And that's where we want to disseminate our results as well. So concluding my talk, we have a summary that we provide a Modelica physical compressor model for a reciprocating and a rolling type compressor in Modelica. As a next step, we could imagine to implement a scroll compressor as well. We could prove fluid dependency in our calculations, which were validated against literature data, which you can read in the paper. And we are able to calculate performance maps with respect to off-design modeling to use it in a faster way than only with the speed of real time. As an outlook, we want to further validate our compressor models, not only to literature, but we have a compressor test stand in our research facility. So we try to adapt the model to other compressors as well. Therefore, we need some kind of optimal experimental design for model calibration to be there as fast as possible as well. And you will see on the heat pump conference in Jeju in April, the integration of this model in an integral heat pump model. With this, I want to close my talk. I thank you for your kind attention, and I'm happy to answer your questions.
Thank you very much, Christian. And Well, we are short of time, so I think we will accumulate the questions, maybe to some of the questions to the end of the session. But yeah, just one question is, I think it's important. You are trying to get a good accuracy in the prediction of the model. So you mentioned that you have a test rig, so it is important, as you've mentioned, the validation. So you intend to do a validation, but also measuring. I mean the pressure and temperature instantaneous in the volumes?
Mm-hmm. We have a fully automated test stand to measure all inlet and outlet states. We have the temperature of the compressor, but we have no inlet states yet. Therefore, we need an adaptation of our new compressor model. So we need to do some adaptations there. But I talked to Mr. Navarro before, and maybe we have some synergies there to have a cooperation, like an exchange of ideas there.
What I mean is that if you need to validate an unsteady, model as yours, you need, recording of with pressure transducer is essential inside the volume in order to register the instantaneous pressure diagram and then validate the calculation. That was my question. Okay.
Okay.
Okay. So. Now it is time to move into the second presentation that will be given by Dr. Rane from the City University of London. Please, Sam, whenever you want.
Thank you, Professor Corbin. So our talk today is on 3D CFD modeling of twin screw expanders, and we are dealing with real gas equation of state, comparing it with RefProf fluid library. The work has been done as Center of Compressor Technology at City University of London. So briefly, I'll go through the introduction of how real gases or their models could be used with the twin screw expander CFD model. A few points about the CFD model itself and the solution approach. And typically, the rotor grid generation is a critical element in this aspect. Then we will talk about the results in terms of expander performance, how they differ between the real gas models for the fluid and compared with RefProf in terms of pressure, temperature, and local property distribution. Also, what kind of deviations are being observed when we use the real gas model, followed by the summary. So to talk about twin screw machines, they are being widely used in the organic Rankine cycle systems for power generation in the range of 50 kilowatt. And their computer models, whether it is thermodynamic model or a CFD model, commonly use the RefProf database to evaluate fluid properties, because this is readily available and is accepted as a universal standard in terms of the accuracy of the properties. However, because CFD models are of iterative nature, when the RefProf database is introduced into the CFD model, it results into a very heavy use of computational time. On the other hand, if we see in literature, there are a number of cubic equations of state, such as Redlich-Kwong, Sauvé-Redlich-Kwong, Unger-Redlich-Kwong, and Peng-Robinson, which define the properties of the fluid in certain operating range, but are considered to be much more faster in terms of estimating the properties. So there were threefold objectives of the analysis. First was to evaluate the computational accuracy in prediction of the performance when these real gas models are used in place of RefProf. Second was how the local properties vary and to validate them with respect to RefProf. And third was the computational time requirements to evaluate that in terms of real gas equation and RefProf. A little bit background to the real gas equations of state. Up to 1850s or so, the ideal gas equation was the only available. But for the first time in 1873, Van der Waals introduced a modification to the ideal gas. And that modification consists of two terms, which is also highlighted here. The factor B, which comes in place of the volume, is an adjustment for the overestimation of pressure that was observed with ideal gas. And there was a secondary factor, which is in terms of A, that was introduced to account for intermolecular attraction. So these modifications in the ideal gas equation of state proved to be beneficial in improving the accuracy, but they were not still accurate enough because they still considered a finite or a spherical shape of the molecule and not the intermolecular forces. So in 1949, Redlich-Kwong introduced a modification to this van der Waals equation, and what he proposed is the equation of state as a function of critical properties of the fluid, such as critical temperature and critical pressure. So with this modification, what we see is the isotherms over a PV diagram came close to the saturation line and what is expected, especially in the pure gas state. They are quite accurate, but when we approach the critical point, they are less accurate, the Redlich-Chong equation of state. So this equation of state was further modified by other variants such as Sauvé-Redlich-Chong, Peng-Robinson, and Unger-Redlich-Chong. And that modification also involved one more parameter, which is the eccentric factor of the particular gas. So with this eccentric factor, what you can see is also at the critical point, the accuracy of the equation of state improved. So we have to ignore this two-phase region and look at what is happening to the liquid phase and the gas phase in terms of evaluation of properties. Looking at twin screw expander, so we have taken our standard geometry case here, which is a combination of 4 lobes and 5 lobes of the male and female rotor respectively. And we have looked at several fluids such as R245FA as the standard refrigerant which was in place, and then alternatives with low GWP values such as 290, 1336, and 1233. The CFD model uses a fundamental governing equation for conservation of mass, momentum, energy. And in addition to that, the moving deforming grids have to be also accounted for because this is a system of positive displacement. So that is taken care by an in-house code, which is used for generation of the grid, which is called as SCORG, stands for Screw Compressor Rotor Grid Generation. And I'll skip this part due to time limitation, but if you want details, which is available in the paper, you can kindly refer to that. A typical axial cross-section and its deforming mesh looks as you can see here. And a verified size of the mesh was taken for this computation. In terms of cell quality, average qualities have been reported in the paper and they were accepted by the NCCFX solver which was used. Now, coming to the results, we have first evaluated using RefProf because that is the basis that we have. And we have looked at various speeds and various built-in volume ratios with R245FA and looked at the pressure and temperature distribution. So this animation here shows a local variation of temperature. It varies from about 60 degree to 95 degree over the entire range. And within the expansion chamber, you can see a local distribution of temperature. On this particular slide, you can look at the performance data. So what we are seeing here is RefProf data with flow, power, and specific power. And then this has been compared with each of the equation of state, also with ideal gas law. So in the cubic equation of state, we can see that the maximum deviation is with Redlich-Chong, and it is, although 1.27%, which is very small compared to practical requirements, but the ideal gas is deviating quite a lot. It can go up to 10% deviation. Local variation of fluid properties and temperature can be seen here, and the maximum deviation was within 3% for temperature. For specific volume, it was within 5% for equation, real gas equation of state. Here, the P angle diagram is seen, and it can be accurately matched between the real gas equations of state and RefProf. Further, two low GWP alternatives were considered for R245FA, especially R1336 and 1233, and similar observations of performance deviations were calculated here. In addition, it is required to be pointed out in terms of computational time requirement that all real gas equations of state took about 4 hours per revolution, whereas RefProf required about 6 hours. So that was a 55% more computational time requirement. And that was consistent across various fluids. So this allows us to summarize the work in terms of computational accuracy. The prediction of expander performance and local variation is quite accurate with the real gas fluids. It should be noted that this is a strict operating range that has been considered. SCORG grid generation tool and NCCFX solver has been used for the study, and whereas RefProf was integrated with the solver in terms of tables. R245FA and few low GWP alternatives were considered, and all of them showed a consistent matching of performance in terms of RefProf database, and also the computational time required with real gas equations of state was about 55% lower compared to RefProf. So this brings to an end of my talk. I would like to thank you for listening to the talk and also welcome you for the 12th International Conference on Compressors and Their Systems at City University, which will be held in September this year. Thank you.
Thank you, Dr. Rane, and thank you for very brief presentation, but I think very good summary of your work.
Thank you.
I have some, let's say, quick questions. One is, so about the leakage, are you able to calculate, or have you validate the leakage in between, in between the different volumes in a way with some experimental? So do you think your calculations provide a good prediction of those leakage?
Yes, we have calculated or validated these results for dry air expanders, not for refrigerants. But in that case, we have a good validation at high speed and low pressure ratio applications. At low speed and high pressure ratio, the leakage is over predicted by the CFD model. That is what we have observed.
Okay. And the other thing is, well, you mentioned there, a mass imbalance, but as a matter of fact, in your calculation, that it takes, several turns of the shaft, let's say. So in any case, this is unsteady. So
Yes.
how you define the mass imbalance? Because there could be accumulation inside the volumes.
No, there is no accumulation because this is a continuously flowing machine. Also, there are pulsations due to transient nature. But what we do is take a cyclic average at the end of a stable solution and then calculate an average mass imbalance.
Okay, so the mass imbalance is due to convergence problems, or let's say errors, let's say, in the convergence, isn't it?
Correct.
Okay, you have in the table, you show a term which is EP. I didn't understand that in the paper. So could you explain what is this EP?
So we calculate the mass flow rate, we calculate the indicated power. And then from the ratio of these two, we calculate specific power. And EP is the error in specific power between RefProf and the real gas model.
Okay, but this is the absolute error or the relative error? This is what, because then you have a percentage. So this is what I didn't understand in the table.
So we use error propagation equation.
Okay, yes, but you mean in the table you saw a value of EP and then you have the percentage. So I didn't understand which is the difference between the percentage and the EP. Is the absolute error EP or?
Yes, absolutely.
Okay. Well, in the end, the conclusion is that the error globally is quite small.
Yes.
So, okay, let's say the idealist equation, the state equation, maybe is too rough, too rude for that kind of calculation. But maybe you could find some kind of a bit better model, not so complicated than the equation of state you are using. What do you think about that? So there is anything in between, let's say the very simple theory and a quite good equation of a state, or not?
All these real gas equations of state computationally were quite accurate, and in terms of time requirement, they were similar to ideal gas law. So I think that is a proposal to use them rather than ideal gas law.
Okay, so in time calculation, so they are similar to the other. Okay, so that's the right thing to use. Okay.
Yes.
Okay. Any of the people, of the other presenters want to ask something, or we have some question for Dr. Rane?
No, we haven't.
Okay, no problem.
Thank you.
So thank you very much. And then I transfer you the chairman job, okay? And,
yes.
And then just, we wait for just 1 minute, and then I will present myself, my paper, okay?
Okay, would you like to share your screen?
Yes, I will do it. Just confirm that you all are seeing my screen now?
Yes.
Okay, with the presentation. By the way, I don't know if you also see, the image with everybody here, with the participants, but I don't know how to cancel it, sorry.
So when you go into full screen mode, we see your slide and just you in the video.
Sorry, I already have the full screen for the presentation. So the thing is, I have to. No.
No, don't change anything. It's all right now.
Okay.
Okay, so that's the right time. So we will start.
Okay.
I would be very honored to welcome and introduce Professor Corbian, who is also the chairing the session. He is going to present on a critical analysis of characterization of scroll compressors, mass flow rate. Just to briefly introduce Professor Corbian, he is industrial engineer by profession, and since 2000, he is a full professor at Department of Applied Thermodynamics at University Politécnica de Valencia, Spain. He is currently also the director of the Institute of Energy Engineering at UPV. He is also the president of Commission B2 of the International Institute of Refrigeration and member of Eurotherm Executive Committee. So, Professor Corbian, please go ahead with your talk. Thank you.
Thank you very much for your accurate and long introduction. Thank you, Dr. Rani. Okay, hello everybody. What I'm going to show you is, well, what we learn when we have analyzed a lot of data from scroll compressor performance. And in this paper, what we are going to show you is which are our conclusions about how to characterize the mass flow rate of these kind of compressors, scroll compressors. Well, the data we have employed is quite huge. The thing is that we were fortunate in a few years ago, the IIR disclosed a big database on compressor performance results that they perform along the program on low GWP alternative refrigerants evaluation. So they tested in different laboratories, different companies, quite a lot of compressors with different refrigerants, and so they disclose all these compressor results. So what we are studying all these results, they are experimental results, and so what we want to analyze is how to characterize these performance results. So we are going to concentrate in this paper, in this presentation, with the scroll compressors included in the reports ARI 21 and ARI 11, which are two Copeland compressors. They are different sizes, and you can see here, different refrigerants they tested. And we also included, a different reference by Cubas and Lebrun, in which they included also tests with a scroll compressor working with 134A. So, normally and usually the compressor mass flow rate characterization is always employing by the standard, by ARI standard, which is the famous 10 coefficients polynomial having third degree. And this is working pretty well and is a very accurate representation. From the very first moment, we also realized that much simpler representation with only 6 coefficients, as the one that already was pointed out by Shao et al. In 2004, was enough for most of the compressors we have analyzed. So this is a first conclusion, is not necessarily the 10 coefficients, but only 6, normally to have an accurate representation for the mass flow rate. Mass flow rate, if we want to characterize that, ideally, the most important thing is to try to do it non-dimensional. So the non-dimensional mass flow rate, as a matter of fact, is a volumetric efficiency that we all work to characterize the compressor performance. And from the very beginning, we know that the mass flow, the volumetric efficiency is basically a function of the pressure ratio, and this has been proven just by theoretical developments. And for instance, just to quote, in the book of Threkel, you can see that they provide, with a theoretical expression for this volumetric efficiency. But there has been a lot, also other authors that even has been as the one that I presented here, Bob Pierre, who presented a very accurate formula for the compressor of the time in the 1980s, which is quite accurate. But the thing is that when we realize this with a lot of data, what we realize is that the volumetric efficiency efficiency is not so easy. You can see here, that for these two tests in which we have all close to 200 test points, so volumetric efficiency is a cloud of points. This cloud of points, of course, we can see the main the trend with the pressure ratio, but we see a lot of scattering due, in this case, these different colors are due to the different conditions at the superheat, at the inlet of the compressor. These are constant superheat or constant suction temperature at the inlet. So you can see that the main trend is clearly, a function of pressure ratio, but there are other things inside. If we see this just plotting the same results, volumetric efficiency versus pressure ratio, for instance, here, this is for the ARI 21 report. We can plot it having in abscissa, in x-axis, the condensation temperature for given evaporation temperature. So we see a lot of scattering in this kind. Of course, there are a big trend, which is linear, but there are other influences, which are different to catch up. Because you see here, the parts are linear, other parts we see behavior which is non-linear. So we have some curvature, some peaks. This is not easy to correlate, okay? So instead, if we plot the mass flow rate for these two sets, you can see that the characterization of the envelope of the compressor is really fine. So we have a lot of points. Here you have the 11 and the 21 report, and you see here, the classical representation based on condensation and evaporation temperature. You can see that it is a quite flat behavior. These are the isolines in these graphs. And if we plot this in a 3D plot, we can see a very interesting thing, that as a matter of fact, the mass flow rate versus evaporation and condensation temperature is a quite flat surface with some curvature, but we can see, that basically in scroll compressors, and this is a first important conclusion, you can see that, the mass flow rate depends on the evaporation temperature. So this is the main influence, and that the condensation temperature only have a marginal influence, and it is not linear. You have here some curvature of this flat thing. Okay, so this is an important thing, but the thing is, of course, this is a quite smooth surface. We do not need a lot of coefficients to correlate this kind of surface. This is something that we wanted to study. Here, and what is the influence of the refrigerant? This is the same compressor, plotted, tested with 4 different refrigerants. You can see that if you plot the mass flow rate, of course, the mass flow rate will be dependent on the refrigerant, but you see that the surfaces still are smooth. And they are quite similar in shape, let's say, although the level is different. One thing that we have found is that if you plot, instead of plotting the mass flow rate versus the evaporation and condensation temperature, you plot it versus the evaporation pressure and the condensation pressure. It is very interesting to see, and this is one of the findings that we have in this paper, that, the surfaces become much flatter. They become quite linear as a function of the evaporation pressure. And, this correlation is much easier than if you do it versus temperatures, which has been the classical characterization procedure. Still, you see an influence of the different refrigerants, but you also see that the influence of the refrigerant is smaller if you plot it versus the pressures and not versus the temperatures. So this is a first finding in our work. Of course, the thing is, what kind of correlation we need to correlate the scroll compressor's mass flow rate. So you do not need, you see the surface, you do not need the 10 coefficients polynomial by ARI. So what we have tried is to simplify this and to see which is the minimum number of coefficients you need. And we have seen that, just a correlation with 2 linear terms with the evaporation and condensation pressure is enough to provide a good correlation of this kind of surface. So in the paper, you will see a full comparison between these 3 coefficients, 4 coefficients, just including a cross term in between the 2 important pressures, evaporation and condensation. And as a reference, what we have what we have placed is the Shaw correlation, which, as I mentioned, is just a reduction of the ARI polynomial with only 6 coefficients. The thing is, even this very simple correlation with 3 terms works very well. If you want a bit more accuracy, you can use these 4 coefficients. And this represents very well this kind of performance. You can see here, just as an example of how good the results are. So you can see here, for, with only 3 coefficients, this is, they are here almost 200 points of mass flow rate. And this is, the comparison between the experimental mass flow rate and the predicted with this very simple correlation with only 3 terms. You can see maximum relative error is 1.6, and this is always a very low mass flow rates. And the RM is very low. You can see that even in this case is 0.6 kilograms per hour when we are talking about in a compressor with more or less 120 kilograms per hour. So it is really impressive that only with 3 coefficients we are able to characterize very well this. If you want to, this is the characterization with the SAW correlation, which has 6 coefficients, and you still see that, more or less the representation is the same. And this is for IIR 11 report, which is working with 14A, so this is for midterm. If you go to a compressor which normally works at low temperature, as it is the 21, this compressor working with 404A works at minus 20 degrees evaporation temperature, so it's a low temperature compressor. And so you can see that it's still in this kind of compressor with high pressure ratios, only with 3 coefficients, we got a very good representation of the compressor mass flow rate. So, and this is the same with, finally, we got this data with from a paper from Cuevas and Lebrun. And, here you can see that the correlation has increased the error. Still, maximum relative error is 3.9%, but this is probably very close to the uncertainty of the measurement. So it still is a very good representation with only 3 coefficients. So let me go into the conclusions. So I think when the compressor is measuring a wide range, as we have had the opportunity to have in these ARI reports, so the thing is the volumetric efficiency has a complex shape. It's not very easy. So we have a common trend, which is linear, but the other trends are very complex to represent. In contrast, the compressor mass flow rate is a smooth surface, so it is much easier to characterize than the volumetric efficiency. So if we want a simple correlation or a good correlation, even accurate, so it is better to directly correlate the mass flow rate, which is what we have done always with the ARI standard. But for scroll compressors, it is clearly that it is not necessary to employ this 10 coefficients polynomial of the standard. So for scroll compressors, we have checked all which we were including this data disclosed by ARI, and we can tell you that the South polynomial is enough. And also, if you want to correlate it, this is an important finding. If you correlate it versus the pressures and not versus the temperatures, you can have very good correlation with only 3 or 4 coefficients. And this is it. Thank you very much for your attention.
Thank you, Professor Corbian. Let me first check if there are any questions from attendees. So there seem to be none. Let me ask the panel members here if they have any questions, any of them. Doesn't seem like. Okay, so let me take this opportunity then to ask you a few questions. Thank you for the nice work. And it seems that a lot of experimental work has been involved in getting this data, which is quite relevant and useful for the industrial community. I have 2 questions. The first one is related to your proposal of using mass flow rate for correlation rather than volumetric efficiency. So when doing this, how would you account for different size of machines? Because volumetric efficiency essentially normalizes the size of machine. So how these correlations would be valid then if you use mass flow rate?
Yeah, thank you for your question. Let me just go back. I don't know. Are you still seeing my
No,
screen?
you need to share again if you want
Okay,
to show any slide.
sorry. Okay, So the thing is that, you know, for volumetric efficiency, you know, the non-dimensional, you know, the size of the compressor is in the theoretical, let's say, displacement.
Yes.
You can use the same when you characterize MREF. So I mean that the interception and the other coefficients of the mass flow rate correlation, it is a linear correlation. You just have to divide it by this displacement. So it is exactly the same. So, I mean, so you can correlate directly mass flow rate, and the coefficients will be divided by this displacement.
Okay.
Okay.
So it's just the scaling of coefficients.
Yes. Yeah.
Very good.
So
Thank you.
You will still have a very accurate, let's say, representation.
Yeah.
Sorry, I would like just because I forgot, and this is a big mistake. I want to highlight that, you know, Dr. Shrestha from the Oak Ridge National Laboratory. So he's also author of this paper, and he cooperated with us in this research. And this was the lab in which they did all the measurements of these two compressors we have taken into account. Okay.
Thank you. Unfortunately, we have run out of time, so I'll hand it back to you as a chair. Thank you very much.
Thank you. Thank you very much for your help on this. And with this, what we are going to do is to pass to the next presentation that will be given by Professor Emilio Navarro from the Universidad Politécnica de Valencia too. And he's going to present a paper with title is Characterization Methodology for Vapor Injection Scroll Compressors of Variable Speed. So Emilio, if you want, please share your screen and then place the PowerPoint in presentation mode. Okay, I can confirm you that we are already seeing your screen, and now it is on full screen mode.
Can you hear me?
Yes, we hear you.
Okay. So, good morning to all the attendants, and thank you for your introduction, José Miguel. And what I'm going to present now is an approach in order to be able to characterize vapor injection scroll compressors of variable speed. Basically, in order to motivate the problem, what we would like to make a short introduction of it. And I think that most of you know that for single-stage compressors, usually manufacturers provide the RV polynomial in order to estimate the mass flow rate and the power input at different evaporating and condensing temperatures. Nevertheless, when we go to vapor injection compressors, the characterization process is more complex, as we add two additional degrees of freedoms, the intermediate pressure and the intermediate superheat. So, and in addition, also we have to measure, we also have to supply the injection mass flow rate in order to have a whole description of the compressor. Therefore, if we want to perform a detailed characterization of this kind of compressors, the number of experimental points that we have to measure increase in a very significant way, as for each evaporating and condensing pressure, we have to measure the compressor performance at different intermediate pressures. This is more or less solved in the standards, like using an approach in which the compression characterization process will be not system independent anymore, and we will try to assume a system in which the compressor is going to work, like an economizer of a specific size, or like an economizer with a specific delta T, temperature delta T. This also has the problem that when we want to characterize these compressors in a calorimeter test bench, we have to proceed with an iterative process that is quite time consuming. So from all these limitations, there is an obvious question from all these limitations, which is related that if it is possible to characterize a vapor injection scroll compressor in such a way that the amount of performed tests will be not so huge, and also that the information that it will be supplied from this characterization process will be independent of the system in which the compressor is working. So In order to try to answer that question, there was a work published 3 years ago by Tello et al., in which they determined that the answer to this question would be possible if there is a function. If there is a function in which we can relate the injection mass flow rate with the different external variables of the system. I mean, the evaporation mass flow, the mass flow rate through the evaporator, the evaporation pressure, the superheat, the condensing pressure, the injection pressure, and the intermediate superheat. And in that paper, they proposed the following linear relation between the injection mass flow ratio and the injection pressure ratio in such a way that we can characterize the vapor injection compressors independently of the system in which they are working. In this correlation should be an additional equation that we should supply to the common Airy polynomial, and in this correlation we have to characterize the coefficients A and B, which will be dependent on the compressor design and also on the compressor and on the used refrigerant in the compressor. So with these concepts fixed, now the objective of the work is to evaluate the possibility of extending this correlation to variable speed vapor injection scroll compressors. And in order to do that, what we have done is to test a vapor injection scroll compressor of variable speed of 100 cubic centimeters tested with propane as refrigerant, or using propane as refrigerant, and also we have incorporated to this analysis the published data from 2 different vapor injection scroll compressors of variable speed working with 410A, and the tests of these 2 vapor injection scroll compressors were developed in different labs and with different compressors. So they are more or less independent one from the other one. The experimental setup that we have used in order to perform the experiment with the compressor working with propane has been follow this scheme. This test rig is ubicated at the Technical University of Valencia, and basically it's a calorimeter test bench in which we have incorporated an injection line in which we have an expansion valve, and we have a base plate heat exchanger with a secondary water loop in such a way that we can control the heat exchange in the injection line. So here you can see a more detailed scheme of the system that we have used. In addition, it should be commented that we use 2 Coriolis in order to measure the mass flow rates, one to measure the mass flow rate from the condenser and the other one to measure the mass flow rate of the injection line. And the mass flow rate at the inlet of the compressor is determined by the difference between the mass flow rate in the condenser and the mass flow rate in the injection line. So based on that, we have performed this test campaign in which we have measured this compressor working at 4 different speeds with an intermediate superheat of 5 Kelvin degrees and superheat at the outlet of the evaporator of 10 Kelvin degrees. And the results that we have obtained for this compressor are shown in this figure, in which we have represented the compressor efficiency and the volumetric efficiency of the compressor as a function of the pressure ratio. It can be seen that there is a significant dependence on the compressor speed of the volumetric and the compressor efficiency. Then going to the characterization of the injection line, we have represented in this figure the injection mass flow ratio as a function of the injection pressure ratio. We can see when we check the validity or the variability of this correlation that for each speed, these correlations seems to reproduce properly the behavior of the compressor. But what we can observe from this representation is that the coefficients A and B depend on the compressor speed. Okay, so trying to go a little bit more in deep on this analysis, what we have done is to represent the coefficients A and B as a function of the frequency. And what we have observed is that there is a more or less linear relation for frequencies from 50 Hz up to 120 Hz for the parameter A and from the parameter B. Also, we can assume, although we don't only have 2 points, we are going to assume that we can have also a linear trend, a different linear trend for compressor speeds lower than 50 Hz. But I assume that here we only have 2 points. Based on that, we have assumed that the parameters A and B depend on the frequency in a linear way, following this relation. And we have performed the fit of the values A0, A1, B0, and B1. I mean, we have calculated these values, we have performed the fit, and then we have represented in this curve the injection mass flow ratio predicted compared with the injection mass flow rate calculated. And the error that we have in all the cases is lower than 10%. As we know that we don't have enough data with the performance experiment that we have developed, we have go to the literature and we have analyzed the data published by the work of Dardenne in 2015 with a vapor injection scroll compressor of variable speed working with R14A, and also the data published by Desden in 2019. In the results, we have analyzed the results from Dardenne, and we have observed that in this case, although he only have a result for the frequencies higher than 40 Hz, we see that in this case, the linear trend is also followed for the parameters A and B, and we don't have this decrease that we have observed before for the frequencies of 50 Hz. And then when we observe the results obtained by Deschen et al. In 2019, in this case, we have a huge amount of data, more data in the work in the previous work of Dardenne, and we have observed that here we observe similar behaviors to the one that we have obtained previously for the propane compressor. So based on that, we have performed the corresponding fit for the data of the Dardenne and for the data of Deschen with this correlation, and the result that we have obtained is that in all the cases using this correlation for the three compressors, the mean square error is around 5%, the mean square error, and the correlation coefficient is 0.99, almost in all the cases. So based on that, the main conclusions of this work is that from the test campaign that we have performed for the variable speed vapor injection scroll compressor, it was identified that the injection mass flow ratio and the injection pressure ratio are linearly correlated for each frequency. But based on these results, we have proposed this dependency of the parameters with the frequency, this linear dependency. We have evaluated the variability of this correlation with two additional vapor injection scroll compressors, and the results always show a mean error around 5%. So also we have to admit that probably we need more information in order to gain some confidence on the correlation that we are using. The results are not bad. And finally, we would like to add that this methodology can be useful a useful tool for compressor manufacturers when they try to provide information about their compressors to the system designers in order to estimate the performance of the vapor injection scroll compressor for a particular application. And also it could be helpful in the modeling approach in order to define new control strategies based on the control of the intermediate pressure. So thanks for your attention.
Okay, thank you very much, Emilio, and thank you also for keeping the time. I have maybe Dr. Rane could check if there is any question sent to Slido, but for the moment, I would like you to also comment on the difficulty of characterizing this kind of compressors, because let's say the large number of parameters, if you want to test them and characterize them using a full factorial test matrix. So I mean, even the standard is not clear how to characterize this compressor. So I would like to compare, let's say, the correlation you have found with, let's say, the normal characterization of this kind of compressors.
Mm-hmm. Well, the point is that the normal characterization of these compressors, they usually propose that you install an economizer, and work with that kind of system, or in case that you don't have that economizer, you have to check the compressor and perform an iterative process calculating which would be the intermediate pressure for a given condition in an imaginary system, in such a way that for each evaporating and condensing pressure, you only have one intermediate pressure, which is the one in which you have characterized it. And with this correlation, what you can do is to know if you couple to this compressor to a different system with a different intermediate pressure, you are able to predict in a better way which will be the behavior of the compressor.
But the thing is this, that with the usual procedure, the thing is that they characterize with a given economizer. So the thing is that that is not general, and this is what you also like to do characterization with is more general for any system. Okay?
Exactly. You have, for instance, a flash tank. This characterization process will have a different intermediate pressure, and the prediction of the compressor performance is more difficult.
Okay, if we have time at the end of the session, I will ask you also to give a small explanation about why this different behavior of the coefficients with the frequency from, let's say, below 50 and above 50. That we will come to that. Okay, if we have time. Okay, so it is time to move into the final presentation that of this session that will be given by Dr. Volodymyr Trandafilov, who is working at the Odessa National Academy of Food Technologies. And who is going to present a paper titled Process Simulation and Analysis of a Rotary Vane Gas Refrigeration Machine for Cold Production in the Medium Temperatures Level. Okay, so Volodymyr, I know that we have a pre-recorded presentation, so I ask the organization to play it, okay?
Okay.
Good afternoon, dear colleagues. My name is Volodymyr Trandafilov. I represent Odessa National Academy of Food Technologies, V.S. Martinovsky Institute of Refrigeration, Cryotechnologies and Ecoenergetics, Department of Refrigeration and Air Conditioning. The topic of my presentation is process simulation and analysis of a rotary vane gas refrigerating machine for cold production in the medium temperatures level. At present, there is a need for refrigerators with a relatively low cooling capacity, about 10 kilowatt, at a temperature level of 0-100 degrees Celsius. Such type of refrigerators can be designed on the cascade vapor compressor refrigerating machines (VCRM). Gas refrigeration machine which the Stirling cycle implements can be an alternative to VCRM. In addition, Stirling refrigeration machine (SREAM) are based on the reciprocating motion of the pistons realized by a crank mechanism. The complexity of the system cranks and levers limits their widespread use in piston stream, among other reasons. The purpose of this study is to create and improve a more efficient refrigerator, a rotary vane gas refrigeration machine, RERAM. Principle of its work, mathematical models of the main processes, energy characteristics and design were considered. RERAM elements and operation. The RERAM consists of two working blocks, W1 and 2, in which the working fluid is compressed and expanded with a 45 degrees shift. The working blocks have one common drive shaft 3. The cooler 6 and the refrigerator 7 are connected to the working blocks by lines of compressed high temperature and expanded cold working fluid. The heat rejected from it by the coolant through line 16 connected to the multi-flow heat exchanger, 3 streams 6. A heat supply line 17 from the heat sink is connected to the multi-flow heat exchanger. Two diametrically opposite vanes are installed inside each W. The vanes 4 and 5 in first W form 4 work chambers 8, 9, 10, 11. The same vanes in second W form the working cavities 12, 13, 14, 15. The cavities of W1 and 2, the lines of the cooler 6 and the refrigerator 7 are sealed and filled under excess pressure with a gaseous working fluid, such as helium. Fig 1 and Fig 2 show how the working fluid compression and expansion occurs in cavities 15 and 9. Gas compression in the cavity 15 W2, process A, B. The displacement of gas from the cavity 15 through C in W1 point. Heat rejected to the environment from the cooler 6. Suction gas cooled to from C in the cavity 9 of W, where when the gas contacts in 9 of the cold vanes, it is cooled in the process B, D. Expansion of the gas with its simultaneous cooling and implementation of external work, process D, E. Gas injection from the cavity through R in W2, point E. Heat supplied to the gas from the cooled object in R. Gas suction from R to the cavity of 15 W2, where it is heated in contact with hot vanes in the process A. Construction of motion conversion mechanism. In developed RERAM motion conversion mechanism, MECM is used which is described. MECM turns the drive shaft rotation into the rotational oscillatory motion of the rotors with vanes. The mechanism consists of a rotating rhomboid and a fixed disc with a profiled raceway. The workflow in rearm is organized so that the angle feed between the axes of the levers of the blades varies cyclically within the specified limits. In the developed rearm, the profiled disk contour of the mechanism with a rhombic drive is described by equation. Dependence 2 is the basis for the mathematical description of the kinematics of the mechanism for motion conversion of the vanes in the rearm working blocks, which affects the nature of the processes implemented in it. Development of mathematical model of working process of rotary vane gas refrigerator. Let us first to analyze the rearm energy characteristics, which implements an ideal cycle. Then, to determine the rearm characteristics as close as possible to those of a real machine, consider its cycle with the diabatic processes of gas compression and expansion. Changes in cavity volumes in W. Considering the design dimensions of the rotor vane group for refrigerating machine and the parameters of the conversion movement mechanism, the law of variation of the cavity volume between the vanes is derived from the equation 2 depending on the angle alpha and the following. Changes in the volume of cavities in one revolution of the drive shaft, see Fig. 5 are presented for the cavities of the two working blocks of the rear arm depending on the angle of rotation of the drive shaft. The volumes at the nodal points of the cycle, in which the beginning and end of each process correspond to the drive shaft rotation on 45 degrees. Cycle of idealized machine. Cooling capacity for rear arm with a drive having a rotational speed n min -1. The amount of heat rejected from the cooler into the environment. Having expressions for K and CAC, found rear arm idealized coefficient of performance. It follows that the cooling coefficient of an idealized Stirling machine and rear arm is strictly equal to the refrigeration coefficient of the Carnot cycle. It is caused by the fact that in deriving relations 4 and 5, the losses from irreversibility were not taken into account. We define, using 4, such characteristic as cooling capacity. The derived value shows that in idealized rear arm it is possible to reach the cooling capacity about 10 kW at equals 173 K, minus 100 degrees Celsius. Figure 6 represents rear arm cycle with isothermal and adiabatic gas compression and expansion processes. The cycle is implemented in the range of average planimetric temperatures. How does pressure vary with volume change during adiabatic expansion can be described as: during expansion process the temperature varies according to the law. Let us work out the relationship between the pressure and volume of the utility during adiabatic compression as well, equations 10, 11. The work done during compression and expansion processes of the working fluid can be represented by certain integrals, equations 12, 13. For work done in the thermodynamic cycle we have finally equation 14. Power at the specified frequency of shaft rotation N will be equation 15. The cooling coefficient of the cycle with the adiabatic processes will be equal to equation 16. Theoretical research of efficiency indicators for rear arm. Here are some of the results obtained using the formula 8, 11. The expansion process in rear arm proceeds at an angle of rotation of the output shaft from to 180 degrees. During the expansion process in the cavity, the pressure and temperature vary from 135 degrees equals 12 to 180 degrees equals bar, and from 135 degrees equals 173 to 180 degrees equals. The compression process proceeds in rear arm at 0 to 45 degrees an angle of rotation of the drive shaft. The pressure and temperature are equals 5 bar and equals 300 at the start of the compression process. It results in pressure and temperature vary in the cavity from 0 degrees equals 5 T, 45 degrees equals 20.5 bar, and from 0 degrees equals 300 to 45 degrees equals 525. Results of mathematical modeling of the rear arm cycle. Table 1 shows the indicators of the rear arm performance evaluation, obtained as a result of mathematical modeling. As noted, the developed rotary vane gas refrigeration machine has several advantages. Refrigeration machine can achieve a high efficiency level in the moderate cold produced. Table 2 shows the results of a parameters comparison for the serially produced Stirling refrigeration machine with rear arm. At the same cooling capacity 12 view, the efficiency of the rear arm is higher by 15% in comparison with the piston serially produced Stirling refrigeration machine. By Massachusetts characteristics, rear arm compared with CP-1, Stirling cryogenics 2.5 times less than, and compared to SREAM -90/100/80 Gellimash 15 times less than. The search for compactness in rear arm is the goal achieved, 510, 516, 300 LWH. The rear arm performance analysis has been done with the use of various working fluids, helium, nitrogen, methane, at a temperature level of 233 K. It is proved that for each from working fluids the cooling capacity increases with the shaft rotation frequency vary and the charging pressure increase. For helium use, the cooling capacity is 13215 watt, and the cooling coefficient E equals 1.656. When using nitrogen, the cooling capacity is decreased to 9156 watt, which is 30% less compared with the helium use, and the maximum value of E equals 1.54, which is 6% less than for helium. Due to all these advantages, both CAD systems and key systems were used at the design stage of the rear arm layup. The design of the two-block solid model is presented on the slide. To calculate the dynamics of rear arm, to obtain the necessary equations of motion, the rear arm model is analyzed using the key system Cosmos motion. Slide shows assembly and disassembly of elements of the rear arm using the key system. Conclusions. The research done allows to develop theoretical bases for calculation, design and construction of rotary vane gas refrigerating machine intended for the cold production at temperature level from 0 to -100 degrees Celsius. A set of scientific and applied problems that are relevant for refrigeration technology has been solved, allowing further improvement of the design characteristics for these machines, reasonably choosing and implementing the optimal modes of their operation. The main results obtained during the execution of this study can be formulated as follows. First, the orientation on the stream rotary vane design eliminates the drawbacks of traditional Stirling machines.
In addition, the rotary vane machine has significant reserves for their further improvement in order to create a generation of new efficient and reliable refrigeration machines.
Second, the mechanism used in the studied refrigeration machine to convert the rhomboid rotation into the rotational oscillatory movement of rotors with vanes ensures the harmonious nature of smooth movement without vibrations, changes in the volume of cavities in two working blocks connected to each other. Third, work processes in rear arm are described by a system of differential equations that do not allow their analytical solution. To determine the energy characteristics of the refrigerating machine, a mathematical model was developed and implemented for describing working processes that take into account the variability of gas Massachusetts in paired cavities and changes depending on the angle of rotation of the drive shaft, pressures and temperatures. Fourth, the ratio of the equivalent working volume to the volume of the machine, the coefficient of compactness of the main volume of the rear arm, as compared to traditional Stirling refrigerating machines, will be at the level of 15–20%. Fifth,
analysis of the losses from thermodynamic irreversibility in the rear arm shows that it is necessary to reduce them to ensure the highest possible intensity of heat exchange between the working fluid of the machine and the upper and lower heat sources.
For this purpose, a cooler and refrigerator must be made in 4 multi-flow plate fin heat exchangers, 3 streams. Sixth, comparison of machines for the main characteristics showed that helium is no alternative. So, when converting a machine from helium to nitrogen, its cooling capacity decreases by 30%, and the maximum value of the coefficient of performance decreases by 6%. When methane is used, the cooling capacity is 9% less than in helium rear arm. Seventh, in Stirling refrigerating machine, heat recovery is organized in the isochoric process. This process is implemented in the regenerator of the machine, which has a heat-intensive nozzle. In the design of rear arm, the quasi-isochoric process of heat recovery is carried out using the heat-intensive Massachusetts of the 2 vanes of the machine. This allows you to create a continuous movement of the flow of the working fluid towards each other in the cooler and refrigerator. Eighth,
in order to assess the life cycle, rear arm analyzed the impact on the environment. The main stage.
Okay, Volodymyr, I guess the recording has finished, isn't it?
Yes.
Okay.
I hope this is not longer for you. 22 slides.
No, it was okay, perfectly on time. Thank you. And the thing is that you read it very fast, so it was difficult to follow the explanation.
At first variant, I have 52 slides, but yes, but when I discuss this moment with my chief of department, we smaller with presentation to 52 slides.
Okay. Okay, so let me put some questions to you. Well, first, you mentioned you have developed, let's say, thermodynamic model, and which of course is correct, and it helps you to the, let's say, to the pre-design. But you know, if you want to build this machine, as you already have show us, you know, the different pieces. So the thing is, I think it would be better to have a better model. I mean, and you even mentioned that, of course, you know, characterizing each volume, you require some. Of course, there is a set of different, a system of differential equations that you could program, you know, and solve. So the thing is, why you have relied for the pre-design, I understand, but why you have not developed, you know, a model taking into account, you know, the system of equations in each volume, you know, and the connections and everything, and the heat exchangers.
In the first variant, we have idea, but no, we have idealized for machine. So when we have started, to polytropic machine, to polytropic form. So I have shown my assembly for another type of machine. We in Fortuna have found another question, questions like Penck-Robinson equation for new machine as we investigation. We take in account idealized and polytropical form. So we have this result. Free for, yes, free for in into account, yes, maybe another questions.
Okay, one question is, you state, you know, one of the conclusions is that the helium is not a good alternative, but I do not see in the comparison, you saw it very, very fast. So why you discard helium, which is the most important, let's say, the performance, which is bad, let's say.
In this slide, but in this slide,
you can use F5 on the keyboard.
Because is helium is haven't alternative. Okay. Did you see? Yes.
Yes.
You see me. In this slide, I have shown that gallium, when I use gallium, he has got big cooling capacity from the like nitrogen and methane.
Yeah.
It's comparison for church pressure and rotation speed. As we can see, gallium is the best of another working fluid, and he has got bigger cooling capacity. That's another.
Okay, yeah, that was my question. That the thing is that it just I understood that you discarded helium, so that you say that helium was not a good alternative. But I do not see this in your results. I see that the performance is good with helium. That was my question.
Yes, I understand. Working fluid is for the best for this machine is the hydrogen.
Okay.
But hydrogen is not flammable. Yes, and we use gallium. Gallium not so like hydrogen, but he's better than nitrogen and methane.
Okay.
Yes,
another
when he
thing
says
is,
no, not an alternative, I think he means helium is the best.
Yes.
Okay, thank you, Sam. And another thing is in Stirling machines, you know, the regeneration is very important for the performance. And you say here that that let's say the heat recovery is you rely on the heat intensive mass of the two vanes. I mean, I don't understand. So this is, of course, you know, you need thermal mass to use as I understand, as a recuperator. But the thing is that you need the surface for the heat exchange. So I do not see that the mass of the vane is going to help you in the regeneration.
Yes, as you can see on the slide, in machine we hadn't regenerated as a classical form. It's a classical form, but it's use vanes which includes aluminum material.
Yeah,
and is a quasi-isochoric regeneration. So in investigation, we calculated that thermal conductivity of aluminum and his properties can use it.
That is my question. That the thing is, of course, with aluminum you have high conductivity, but still you need between the gas and the metallic mass, you need a lot of surface. So how you build that surface in the vane, I do not see it. But do not worry. So this is a very specific question. Sorry.
No, it is. I can understand. And
in any case, as in the meantime, while you are looking for the slide, let me just point out that we ended. This was the last presentation, so I think if you agree, Rane, we can also have questions for the other papers, because as far as I understand, our session ends at 12, and so we still have some minutes for further questions. Do you agree?
Yes.
Sam,
yes, we can have a joint open question session now.
Okay, so Vladimir, yes, please. So these are the vanes, yes.
Yes. So thank you for your questions. Area between the vanes and area between the vanes and the corpus to block is figured and angle between the levels using like regenerate quasi-isochoric process.
Okay, but that's theoretical. The thing is, for the heat transfer, you need, heat transfer coefficient, you need heat transfer area. So this is, it is difficult to imagine how you are going to have this in the built in the vanes.
Yes.
But I understand. So the process you look for is the isochoric process. Okay, so
May I ask a question to
yes,
Volodymyr?
please. So there are other questions for this paper?
Yes, I have a question for Volodymyr. So in a classical vane machine, there is an offset between the rotor and the housing, and the centrifugal force drives the vane outward to create the sealing. In your machine, how are you creating this change in volume to cause suction and discharge? Is my question clear?
Yes, I understand. And changes volume in a machine is have in two block, one and second. Question of the leakage, I don't above.
Okay, so it is without leakage.
Yes, I don't above it. Here's a theoretical machine.
And how does this volume change? So which are the components which cause this change in volume?
Change column, as you can see on this figure, he have 1 and 2 blocks, cavities, on first and second one block respectively. Changes have sinusoidal form, and between the cavities is 45 angle between the cavities, 45 degrees.
If you go to slide 2, maybe, where you have a cross-section view.
Cross-section?
Yeah, you can scroll up. Slide 3, yeah. Yes, here. Can you show here, like, how is the volume changing?
Yes, I shown up. If we have one working block, this side is a compression side, yes, and this side is expansion. So if when in this side was section the working fluid in these cavities, rolling into and compression between the vanes, working fluid is the compressed and heat at warm. He is rejecting to a heat exchanger cooler.
Mm-hmm.
When after he is cooling, the working fluid is going to this cavity and at the and in the revolving way, we have changes cavity in this volume, and this is expansion. This is expansion, and gas with low pressure and low temperature going to the heat supply line. To yes.
Okay, thank you.
No, I for this century, is this compression cavity, is this expansion.
Mm-hmm.
So we have 3-4, 1, 2, and 3-4 heat exchanger, plate fin heat exchanger. We use plate fin heat exchanger.
Right. Thank you.
Okay. Thank you, Volodymyr. Well, there are more questions for other papers. For instance, I can ask you some. How do you are you able to take into account the oil sealing in between the two lobes of the screw compressor in your calculations, or do you consider this as a gap in between the two moving parts?
Yes.
No, sorry. That question was for Dr. Rani.
Yes. So so this particular study was with a single fluid. which is the refrigerant. So
Yes,
oil
a
was
single
not considered.
fluid, helium, nitrogen, methane.
Sorry, Volodymyr, this question is for me. So
Yes.
so, but there are other cases where we can account for oil as well between the two rotors. Which
in the
will be a two
CFD.
fluid
And
flow.
yes, so that's
Yeah.
possible. So and let's say this is just a question. I don't know how do you can do this kind of calculation. What I mean is how are you able to model the oil stick to the surface, which is what is producing the sealing. So this is possible to have all of that included in the CFD.
Yes, that is possible. Yeah.
Okay.
So we can include surface tension and sticking effects of the oil on the surface.
And the grid is must be very fine, I guess.
That's a limitation we come across. So the solution will not be highly accurate, but we can include the phenomena.
Okay. Thank you.
Thank you.
So could you please check if there are other questions? And in while you do that, so maybe Emilio, would you like to explain a bit better what I asked you? So why there is this change physically? There is any reason that you guess why this is there is a change in this behavior of the coefficients of the correlation?
You mean, can you hear me?
Yes. Yes.
Okay.
Yes.
You mean in the frequency?
Yes.
Well, we don't have a real explanation for that. We just observe this for our compressor, as there was only one speed at 30 hertz. We thought that maybe this was something particular for the compressor that we were testing, but then we observed that also for this other compressor with 410A, we observed the same behavior, and it is something that at this moment we don't have an explanation for that. Just we observe this.
That is very interesting. So maybe, I don't know. So this is something is happening around probably all the compressors or even the inverter. They are optimized for or designed for a given frequency. And then, the changes up or down, they are changing in a different way. So, okay. So any other question?
I have a question for Christian, the first presenter.
Please, please.
So in the Modelica, how do you include the leakage flow between the sliding element and the roller?
Yeah. So basically, we use the a pressure loss correlation, which we measured once for a compressor, and it's widely applicable to have a resistance there. So we can compute based on inlet and outlet pressure the resistance of the flow, and this correlates to the leakage. But this was also published before by Roscoe et al. We didn't. We just applied it there, so it works very fine for alkanes and for hydrofluorocarbons with their measurement data, and that suits fine our application here. If we want to apply new refrigerants or other geometries, we need to measure them. So this is an information that you not find in literature easily. So
yeah, and it's also a very critical element of the model.
Yes, it is. Indeed.
Thank you.
You're welcome.
Well, as there is no more questions, just I would like, Christian, to mention that we totally agree with, with the kind of modeling you have to use. So it's, on my view, the thing is you can have a detailed model for let's say the compressor development and analysis of the compressor, but this is not the one that you need for the system modeling, because it takes too much time. That's the point. So this is our conclusion too. So the thing is that you can have a detailed model for the development of the compressor, but then what you need is to characterize the compressor. So you have to develop those surfaces, those response surfaces of the performance of the compressor. And this is enough for the system, let's say, optimization and estimation of the performance of the system.
And it was quite interesting. Maybe we discuss it in the break later on. We found something the same as you found, that we just need 3 to 6 parameters to quantify the volumetric efficiency or the isometric efficiency, isentropic efficiency. So we want to publish this as well. So we have a a good benchmark with your findings. So we observe this as well in our experiments.
Take care, because that depends a lot of the, let's say, on the range of the test matrix. So what we have seen, of course, if you only have a few points, and you know, the range is not very wide, so everything is easy to correlate. But when you do, as we found in this data base, you know, we have a lot of 200 points covering the whole envelope of the compressor, then it is not so easy. Both compressor efficiency and volumetric efficiency, they are quite difficult to catch up. And what we saw is that it is quite simple and, let's say, safer to do the correlation for the macro rate, because a lot of times during the modeling of the system, you have to extrapolate, you know, some points, not very far from the envelope, but, you know, to points which have not been tested. And so for that, you know, the less coefficients you have, the more robust the correlation is, and the safer is the result. So we think that these simple correlations are better for modeling of the systems.
Yeah, that's fine. Really interesting.
Thank you. Okay, so it is 12:05, so we should conclude our session if there are not more questions that we should answer. So could you confirm, Sam, that there are no more questions pending?
Yes, on Slido there were no questions, and I think from the panel itself there are no more questions.
So that's perfect. So so then thank you very much to you, Sam, for your sharing, and thank you to all participants, because you have been really good, you know, keeping the time, which we were told that was very essential. And well, thank you for all the presentations. I think it has been a very interesting session, and I hope that we all will be able to enjoy this nice conference. So it has been a pleasure to meet all of you, and so we will keep in contact through the conference and further on. Okay.
Yeah. Thank you, Professor Corbin, for sharing, and to all the participants for presenting.
Thank you, everybody.
Thank you.
So we close with this session, and so see you around the conference. Okay.
Yeah. So there is a break now, and the invited talks will be presented at 1300.